hope so. The first session to everybody just can enjoy with us and sharing the knowledge together. Okay, on this time, I will to introduce to our speaker and the moderator of this session. Start from the speaker, Mr. James J. Miller from NASA. And we are online Dr. Werner Ederer from European Space Agency. And then for announcements to Professor Yusuharu Kuni from Shore University and speaker Mr. Masaya Murata from Japan Aerospace Expression Agency. And on this, may I invite to the moderator of this session, Dr. Suwat C. Sawed, Head of Astrodynamic Research Laboratory of GISDA. Please welcome and please give a round of applause.
Good morning, everybody. Today, it's my pleasure to have a chance to be here, then to be the moderator for this very first session of the day. Actually, I'm pretty sure one thing that this session would be very interesting. The session is on the emerging technology in the new GNSS era, and which is lunar pointing navigation and timing service. Pretty sure this one is a new technology and even the new concept for many of Thai people online and offline, which is being in this room here. All right, let me start with the first question. This is very general question. Like, oh, I have mask. All right. The very first simple question is, what is the Luna PNT service? And yes, and I would like to.
Okay, could you show my slide? Okay, thank you very much for the introduction. So my name is Masaya from Japan Aerospace Exploration Agency. And we are designing the lunar navigation satellite system as shown in the slide, which is a GPS-like navigation satellite system designed for the moon by JAXA. And here you can see the moon. And in short, we will design and deploy the GPS-like navigation system for the moon. So as you can see, our primary target is the South Pole region because the U.S. Artemis project will expect a base camp. They will establish the base camp there at the South Pole region. So our focus is to provide the PNT service at the South Pole region using the navigation satellite system. And our current design is shown here. And we're going to use two stable moon orbits called elliptical lunar frozen orbit. So we're going to use these two moon orbits, which are very stable. And for each orbit, we will deploy 4 satellites. So the total number of the navigation satellites becomes 8 in our design. And among eight satellites, we call these satellites LNS satellites. LNS is a lunar navigation satellite system. So among 8 LNS satellites, 4 satellites are carrying optical and radio frequency communication payloads. So these lunar navigation satellite system, LNS satellites, also function as a data leader satellites between the moon and the Earth. Okay, could you go to the next slide? So our LNS or lunar navigation satellite system, LNS, is not only for PNT, but also for the communication in a cislunar space. For example, the mission data taken at the South Pole region will be transmitted to the Earth using our LNS satellites. So the LNS satellites also function as a data leader satellites. And to achieve the 10 megabps and more, we will use the Ka band. Ka band are shown in the blue arrows here. And if we need 1 gigabps and more, we will deploy the optical communication links as shown in the yellow arrows. So the mission data taken at the South Pole region will first transmit to the LNS satellite and go into the Earth data relay satellites as shown in the yellow arrows. So our lunar navigation satellite system is providing the CPNT service at the South Pole region of the moon. Okay, could you go to the next slide? So the system overview is shown here. So we will provide the real-time PNT service at the South Pole region. And as I already mentioned, we will use two stable moon orbits called elliptical lunar frozen orbits. And for each orbit, we're going to deploy 4 satellites. And these LNS satellites will transmit a navigation message to the South Pole region. Our primary user is a rover exploring at the South Pole region. So these LNS satellites will transmit the navigation message in the same way as a GPS system. So after receiving these messages, the PNT calculation will be performed on both the rover and then real-time positioning will be obtained. So these EL forces are very stable, and we can decrease the number of orbital correction maneuver, like maybe once in a few months or even once in a year. Okay, could you go to the next slide? So this slide shows the LNS satellite constellation for dedicated for the South Pole region, and this table shows the orbital elements. But I will skip the detail. But it's elliptical orbits, and the orbital elements for the 8 LNS satellites are shown here. And one big feature of this satellite constellation is it's going to achieve a very low h-stop at the South Pole region. So this graph shows the h-stop time versus h-stop, and the average h-stop at the South Pole region is around 1.3, which is very low. So I also calculated the GPS h-stop at the Tsukuba Space Center in Japan. It was 1.2. So our LNS satellites just using 8 satellites, but it's going to provide a very low h-stop of 1.3 at the South Pole region, which is very huge feature of our system. Okay, could you go to the next slide? So the big challenge is how to determine the orbit. How we're going to estimate the orbit and the clock of the LNS satellites orbiting around the moon. So the moon is far away from the Earth, like 380,000 kilometers from the Earth. It's very challenging to determine the satellite orbit and the clock information. So we have been investigating several approaches, but we are now focusing on the GNSS navigation technique for the LNS satellite orbit determination. So navigation means a real-time orbit determination. So our LNS satellites will become highly autonomous. So these satellites will estimate their position, their clock in real time using the navigation signal coming from the first side of the Earth. So these signals are called weak signal or side-load signals because the GNSS satellites are all pointed towards the Earth center. Only the navigation signal coming from the first side of the Earth are visible at the moon altitudes. So we're gonna apply these GNSS weak navigation technique for the orbit determination of the LNS satellites orbiting on the moon. And this graph shows our simulation results. And after the filter convergence, we confirmed that the cis error of less than 20 meters could be actually achieved at the moon altitude, I mean in the year of fall. Okay, could you go to the next slide? Next slide, please. So we are now planning this LNSS demonstration mission targeting around 2028. So we're gonna launch one LNS satellite around the moon, and we will also deliver the one LNS receiver at the South Pole region. And these satellite and receiver will be launched by our H3 rocket and using our lander mission. The operation concept that is shown here. So I will skip the detail, but we will deploy the one LNS satellite on the moon, and we will place the one LNS receiver at the South Pole region to actually evaluate the lunar PNT accuracy in the actual moon environment. So this is our LNS demonstration mission currently targeting around 2028. Could you go to the next slide? So as I mentioned, we are planning to deploy one LNS satellite around the moon, and we will also place one receiver at the South Pole region. And this LNS satellite will receive the weak signal from the GNSS satellite and perform the orbit determination. And based on these results, the navigation message will be sent to the LNS receiver at the South Pole region. So we can correct the bunch of the actual data in the moon environment. So based on this data, we will evaluate how accurate we can actually achieve in the actual moon environment. So this is the objective of our LNS demonstration mission. Okay, could you go to the next slide? So this is the last chart of my presentation. So we are not proposing the first ever lunar PNT and interoperability demonstration. Here I used interoperability because this kind of lunar PNT system is not only from JAXA, but ESA, European Space Agency, and NASA are also planning a similar navigation satellite system. For the European, for the ESA, these satellite systems are called Moonlight, and for NASA, this lunar navigation satellite system is called LCRNS, which is a lunar communication relay and navigation system. So in the year of 2028, we expect that some of their satellites will also in the moon orbits, maybe one from ESA or two from NASA. So if we work together, we can have 4 or more navigation satellites on the moon, so we can actually evaluate the lunar PNT accuracy in the actual moon environment. So we are not proposing to collaborate with European Space Agency and NASA to demonstrate the mission. Okay, this is the end of my talk, and thank you very much.
Thank you very much. Yeah, that's just a really good explanation for the Luna PNT service. All right. What I found is a Luna PNT service also do the communication from the moon and the Earth as well. Am I correct?
Could you repeat the question?
The Luna PNT service also do the communication between Earth and Moon as well. Yes, and it's also the main objective is for the robotics, so for the robot to try to explore the moon, and then so that I have another question that I would like to ask Professor Yasuharu Kuni. That what is the robot that we try to develop in this day now? Yes, and then
What is the question?
what is the robot that you are planning to develop in this state in this day currently? Yeah. Yes.
Okay, so please show us my slide. So actually, I'm come from the outdoor field. So no, yes, this is my slide. So next, please. So I'm working for. I'm studying for the unmanned lunar exploration system. So we don't have any GNSS service before because so no one gone before. So this environment is no human, so no one has gone before. So that's why. So we don't have any service from support from the GNSS. So next, please. So, so this is one of my work study. So we are discussing the project for the lunar. So exploration on the moon surfaces. But so this was so we discussed this project more than 20 years ago. So, but it was canceled. But we continued this kind of conventional type exploration robot called Robo. After that project, next slide, please. So, for example, this is our robot. So we are testing this system in the Japanese volcanic island. So this is one of the picture in that field test. So next, please. So I have a lot of type of robot system like this. But so all robot is size of those system is large. So large, it is so difficult to send such kind of system to the moon because so we don't have any, not so many chance to send a large system to to the lunar surface. So next, please. So large system has many disadvantages. One is the cost, and the other is risk. You know, so because we don't have not so many system on the in the environment, that's why so we have to avoid many risks to manage such kind of system. So then, so we decide to create a new exploration system by using a small robot. Next, please. So this is one of the image for next generation of exploration systems. We have many kind of small robot. So we have to control each robot for exploration, but so small robot, it is so difficult to install the high performance sensor and the system into the each robot. That's why so we have to change our scheme for exploration. So next, please. So in our system, so we apply the random behavior on each robot. So because so we don't have a encoder to control the wheels, because you know, so we cannot get a high accuracy for control and measurement. That's why so we introduced the random behaviors. But to keep the robot into the controlled area, so we have one special point called a swarm center. So this is a kind of a marker or simple GNSS system or a radar robot. So each robot just know about the distance from the marker. Then so we designed some kind of stochastic curve, something like in my slide. Then so we can keep a robot into the controlled area. So next, please. Oh, yes. This is the one simulation result. So we can, so don't, okay. So robot can follow the leader robot system. So robot cover this area, something like this, you know. So it is a very good feature for efficiency to find something in the area. So next, please. So now so we proceed, we developed our experimental robot. So this is one of the our robot. So you know, so we can control these groups like this. So next, please.
Let me interrupt a little bit here before we proceed ahead. I would like to invite Mr. James Miller to be on the stage with us. Yes, I would like to invite you to be on the stage with us now, and yes, then yeah, and sorry for the interruption, and then I'll proceed to your presentation.
Okay, so show me a slide. So this is another video from my field test. So this is a new building. So because so currently I'm working with a Japanese construction company. They want to use this technology for investigate or recording their schedule or work. So that's why we are testing our scheme into the new building. So anyways, so JAXA want, so this is one of the JAXA's project. So we are working with JAXA Innovation Hub in this program, in this application. But anyway, so they want to make us our system more robust. So that's why we are applying our system to the actual application. So next slide, please. But so smaller robot has also have another problem. So it is a mobility. That's why we introduced hopping mobility on our small robot. So next slide, please. So this is a fast test, our fast test. So in the initial stage, we have just like a miserable result. Then so we start to discuss about how to hop by our small robot. So next, please. So this is one of the discussion or experimental result. So anyway, so next, please. So then so finally, so we compose our robot system like this. So this is so here is a JAXA's sound yard facility, test facility. So we bring our robot there, then test the mobility of our robot like this. Next, please. So finally, so we developed the actual exploration robot. It is already installed on the Streamlander spacecraft. So this system will be launched in this year. So next, please. This is our robot. Anyway, so I can show you the final result of hopping by our robot. Oh, click and the larger picture. Or push us, you know. Oh, okay. Yeah, this is a result of final result of the mapping mobility. So in this time, so I hope so 6 times of this distance and the height, so we can get on the moon. So next, please. So this is another result. So we developed the another robot by using these technologies. Yeah. So now, so next, please. So we are discussing another project in the moonshot. So next, please. So now, so we are going to the moon to build the lunar city, future lunar city. So we choose go to the cave on the moon. So we have a lava tube on the moon. So we like to explore in the cave. So there's no support from the satellite. So our system have to be a full autonomous function, have to have a full autonomous function. So now so we are discussing about such a system. Next, please. Yeah, so by using our research result. Yeah, that is my final slide. Thank you very much.
One thing that I learned from these 2 presentations is that all the researcher around the globe try to do the moon exploration. So, we have some technical problem technical question from the people online. So the first one is, what is the altitude of the GNSS? Lunar.
Yeah, thank you very much for the question. I think it's about 9,000 kilometers from the South Pole region to the LNS satellite. So about 9,000 kilometers would be the answer for the first question. And for the second question, okay. So this thing, it's difficult to answer right now. So maybe I should answer later after this session, if possible. Is it okay? Okay, thank you.
All right. Then I think one thing that I would like to hear the update on the progress, how we work on this from the NASA sites as well. Could you please
Good morning, everyone. Sound check. This is just in time arrival, as we call it in America, but my Thai friends tell me it's just Thai time. So I'm very happy I was able to quickly make it here. Want to thank my colleagues that presented previously, and I want to check with the colleagues in the back. Are we good to go with the presentation? Okay, I think we can go ahead and put up the first chart. Okay, so this is almost a little bit related to what I presented yesterday, and I want to take a moment just to talk about this particular picture. NASA has a program called CLIPS, or Commercial Lunar Payload Service, which means that companies can compete to get money from NASA to actually go to the moon. And so this particular lunar lander is called Firefly, or Firefly is the company, and it has 10 payloads on it. One of the payloads is the first GNSS receiver ever to land on the moon. So it's a partnership between NASA and the Italian Space Agency. We're planning to go in about 2025, maybe a little bit sooner. The challenge is actually building the lunar lander. We'll be using a SpaceX rocket. But the bottom line is, if we are successful, this will be historic. This will be the first time ever that GNSS signals are proven to be able to be processed on the moon, and it will set the stage for many other types of applications. I'm sure my Japanese colleague talked about a lunar positioning system and something similar. This is actually using the signals that are emanating from the constellations that are surrounding the Earth. So next chart, please. Okay, and so again, I always go back to the policy, why do we do certain things? And many times it's directed for us to do these things by the President of the United States. And so we do have it's P&T, positioning, navigation, and timing policy. And what this last administration did before the Biden-Harris administration is we have Space Policy Directive 7. And I think most people in the room have already heard the space service volume pitch. They understand that from 3,000 kilometers to GEO, or 36,000 kilometers, we do have a service of space that has full GPS coverage. We've brought that into the International Committee on GNSS because more systems are much better than one. And the reason is obvious. You want to enhance that availability. You're going to have additional resilience. And so you're going to make your overall position solution that much better. And so this latest presidential directive actually has us take the space service volume from GEO into cislunar space to be able to serve lunar missions. And we're doing that with close partners. And so at first we're working with the Italian Space Agency, then of course ESA, and I'm sure we will be working with JAXA in the future as well. So very, very important effort. Next chart, please. This is kind of a busy chart, but really what it shows is NASA is a very important user of GPS and GNSS services. And what we actually do is provide additional capabilities to not only our astronauts, but to many people on the Earth. And I think many of you know already, GPS in low Earth orbit is standard. It's now on the International Space Station for many years. It's on Orion. It's on the Space Launch System. Almost everyone is using it. And what we're in the process of doing now is when we do lunar flybys, such as we just did with Artemis, we will record that data and try to understand the availability of the signals in the space domain out that far. So we're building partnerships with the commercial sector as well, such as SpaceX. So when they do similar things, we can compare and contrast the data. So that's one important space operations aspect of GPS. The others I think you're already familiar with. I'll just point out the last one, real-time onboard navigation. Traditional navigation for spacecraft is a combination of techniques, radiometric tracking from the satellites or from the satellite networks. You have optical, you have inertial navigation. There's just a variety of techniques. And the importance of GNSS, it's an always on signal. And it's strange, I've actually been asked by some of the astronauts during the Apollo years, why would you do this? We did not need GNSS when we did Apollo. Well, the answer to that is we do it because it's there and it creates greater autonomy. We can reduce the burden on the communications network and actually have a self-autonomous spacecraft. So next chart, please. And here's a perfect example of that. All of the traditional ground-based and space-based navigation aids. And all we're doing with GNSS is we're complementing or augmenting. And just like in aviation, we begin to use it as a primary way of getting positioning, navigation, and timing. So next chart. Why would we do this? We'll look at all of the ways that we benefit from that. Satellite servicing in the geo belt, very crowded. If you could use GPS to reduce the distances between all of the communication satellites in the geo belt, you're actually creating new real estate. You are always going to have spectrum issues and therefore some spacing requirements. My colleague Dominic Hayes would probably be the first one to tell me that. But once you get over the obstacle of not interfering with each other, then you actually create an ability to put more spacecraft up there. People have heard about our Gateway station that will go around the moon. That will be kind of a landing point for crews that will actually land. And then, of course, it expands from there to actually go on the moon, assuming that we're successful with our LUGRA or Lunar GNSS Receiver experiment, and we're able to expand on that for mobile vehicles and so forth. Next chart. I think most people are familiar with the fact that when we're talking about a space service volume, we're really talking about using the side lobes or signals that are radiating over the limb of the Earth. Of course, the Earth is in the way for many of the applications, but the side lobes are strong enough to get navigation grade performance. And so we capitalize on that with weak signal receivers. And so as the technology continues to progress, we're going to get more and more capabilities. And already with MMS, it's a heliospheric mission, we are halfway to the moon and we're processing 5 to 6 satellites in view. We all know GPS was not made for space applications like that. It's terrestrial, aviation, and maritime. And so we are pushing the envelope with these types of space applications. Next chart, please. Here's just a little bit longer distance so that you can see this actually goes out far enough that if you have a high gain antenna and an ultra weak signal processing receiver, we expect that you will fully be able to process GNSS signals on the moon. And so the first receiver will be both GPS and Galileo because we really do need that enhanced availability. Next chart, please. On the Lunar GNSS receiver experiment, some of you know Joe Parker from the International Committee on GNSS. He works for me. He is a phenomenal PI, principal investigator. And this just kind of gives you a snapshot. I know we're short on time, but a snapshot of the intended time that we're going to be out there actually able to process signals and then compare them once we get that data back. So we've got a long trajectory all the way to the moon. We're going to have at least 12 days on the surface. Of course, it's going to be a very strenuous environment with radiation and so forth, with the cold. But the Italian Space Agency is now building that very receiver. It's at Goddard, and we're putting a lot of our faith into the success of this mission. Next chart. This is just a quick snapshot. We're moving again from terrestrial-based navigation aids to being able to have autonomy around the moon with lunar positioning satellites. We'll have a GPS-like system around the moon eventually, most likely in conjunction with all of us working together through ICG and other forums. Next chart. And here's just kind of a conceptual overview of what that will all look like. We're talking about integrating communications and navigation. You might have a communications satellite with a navigation beacon on it, for example, and also able to provide search and rescue. So the Europeans called their similar system Moonlight. We call ours LunaNet. And in the end, they will all be combined so that we have cohesive cross-support functionality. Next chart. Just real quick, this is where we're at. This is where we're going. And far term, we expect to have quite a few communications and navigation nodes up there. This may be my next chart and last chart because of our time constraints. Just my contact information. So I want to thank you. I'm very grateful that I pushed my taxi driver to get me here in time, and happy to take any questions.
Thank you very much. And then it cannot say complete if we don't hear an update from the ESA side as well. I think we also have our panelist from ESA. I would like to ask him, Professor Werner Endler from ESA. What is the update? What is the update from the ESA side?
Yeah. First of all, can you hear me?
Yes, I can hear you very well.
Okay.
And let me take this the time kind of very short here.
Yeah. Okay.
5 minutes, please.
Yes, I try to do my best. Can you bring up the slides, or shall I share mine? Okay. Are you ready to show the slides?
Werner, we're not getting there we are. Affirmative.
Okay, good. Let's go to the, first of all, thank you very much. My name is Werner Enderle from the European Space Agency, and I try to be on time. I have many slides, but let's go through. Can you go to the next slide, please? This gives just an overview that whatever was saying that we intend to go to the moon and do it together with our partners. And if you go to the next slide, please, because there is, I think, an aspect which means that there is also a huge business in that context to going to the moon. And the vast majority of these is actually that the development beside the transport, the technology development that we are going there. And that means, as we have seen from our colleagues from JAXA or the universities, the developments of this technology and bringing us there and have different type of operations on the surface as well as in the cislunar space. This is a major driver. If you're going right now to the next slide, please. So the next slide shows, this is starting with the Artemis, and this is basically just a scenario, what is upcoming in the next couple of years. We have seen it differently, but important is that All of these activities, they are, for instance, Gateway, which is one of the main aspects there. This is a joint development. And we believe, as Masai was saying, also JJ, one of the key elements is that we have a collaboration here. And using joint standards and making sure that all of our, especially in the early stage, at our system, which are right now, maybe GPS, QZS, or the European Galileo, that they are used to the maximum extent. If you go to the next slide, please. This shows from the European side, from ESA, what kind of contributions we intend to do for the exploration of the moon. And you have different elements there. And if you go to the next slide, please. One of the important part is that we're expecting that at the end of this decade and until the end of the next decade, that major, let's say, activities are really will happen. The total number is 250 plus missions are, let's say, expected to be happen. Many of them simply bringing simply stuff there. And making it possible that the humans can stay for a longer or permanently on the moon. Next slide, please. And one of the, let's say, answers to your question, what is the status, is the following. We, at the moment, the models for, if you looking at the satellites, they each of them using their own navigation system. And what we see, this is basically highlighted on the right-hand side. There is an opportunity, and the opportunity is really to provide services, especially all of the systems needs communication, navigation, and the opportunity is doing that together and contributing to an overall system with the individual systems from the different countries and making sure that they're working together in order to get the most of the benefit out of that. And JJ was mentioning one of them, for instance, of this coordination body, which is the ICG, the National Committee on GNSS, where we're working quite successful together with all the nations. If you go to the next slide. So that means where we are. We first of all, we have identified what kind of different conceptual approach we would like to do, because we have on the right-hand side of the slide the different, let's say, activities there. And what you see on the bottom part, what we believe is, this has also been mentioned by NASA, that we have one aspect, which is we have to work together, not only as the different nations, but also with the public-private partnerships. NASA was mentioning that. And the same story is true for ESA. So that means we are looking to have a joint development in order to provide infrastructure on the moon and around the moon. And some of them, let's say, of these infrastructure will later on be definitely, let's say, provided and operated by industry. If you go to the next slide. This is just showing our start from the European side with the, let's say, we have early missions. And the first mission we have is a joint activity. This is a lunar pathfinder. And this is basically pathing the way and providing very important insights into, let's say, our Moonlight constellation. Pathfinder is intended to start in 2026. And if you go into the next slide, please. The Pathfinder is also therefore for us very important because it's the first time that we're using GNSS together with a laser reflector dedicated to perform a precise orbit determination. We have heard that PNT is normally using on board, but beside the onboard capability, if you go to the next slide, this is the receiver. And here you see that the capability on the tracking, what is position accuracy, what we try to achieve is definitely only with signals below 100 meters. but with a very, let's say, tiny size and a mass compared for this type of missions. And it will be a GPS Galileo receiver, which we will fly. And if we have another, let's say, onboard capabilities, if you go to the next slide, please, meaning that our needs to fly and also later on to prepare for the landing is that we're getting with the Lunar Pathfinder basically let's say results. They are lower than 50 meters in terms of accuracy. But if you do post-processing, we are convinced that we can go below 10 meters. Now, the next slide, as we already said, is if you go to the next slide, please. And in terms of time, if you go to the slide 16, these are just showing some of the elements, the contribution by NASA to the Lunar Pathfinder. If you go to the next slide, please. Yes, thank you. This gives an overview of our Moonlight conceptual. We have basically 4 satellites, and they provide then the services for the communication and the navigation. But in conjunction with the existing ground infrastructure, that means that the space service volume. And if you go to the next slide, please. This is showing just let's say a concept of our high eccentric orbits in order to have basically the 4 satellites together at the end with let's say other satellites from our partners from the international, and they will then bring basically this to a stable infrastructure element which can be used by everyone. Now, I think in terms of time, I would like to go further. If you go to the next slide. If you go to the next slide, please. Next slide, please. Yeah. This is just showing that if you want to go there, we have to find also suitable places where we can land. And this is one of the things which is a difficult situation, but we have the means right now, if you go to the next slide, to really explore new techniques in order to find, let's say, lunar landings locations. And here we have outlined a couple as proposed by Artemis. If you go to the next slide, and this is for us, therefore, an important aspect, because what is finally needed if we definitely want to go down to the moon surface, yeah. And what you see here are different on the left-hand side, different let's say stages. But what is important is that we have a really a very challenging requirement, namely that we have a horizontal position which should be lower than 20 meters, but this is a 3 sigma value. So that means a really challenging. And on the right-hand side, you see that the number of visible satellites. And again, if we can achieve that we have satellites visible from all of the other constellations and partners like JAXA, like NASA, then we definitely are convinced that we can achieve that. If you go to the next slide. This is just to show you basically activities and where we believe that we have definitely significant benefits for our entire space programs in the future. The next slide, please. And this is just ESA-NASA for the, I think, the signature for the cooperation for the lunar exploration activities between NASA and ESA. But I think the next 2 slides, if you go into them, they are therefore important. Next slide, please. There are documents under development or have been released, which are a key element for the technical interoperability. Namely, they're providing standards and procedures. And in that context, if you go to the next slide, please, it is important that we have a clear understanding. And from ESA side, the understanding is that it can be done only if the different, let's say, actors are playing together, so that we are really making sure that we have in the long term a really working and good infrastructure for the different exploration activities from the agencies around the world. And with this, I think this provided the answer to your question, what is the status where we are? We are in full preparation and looking forward also to publish soon or starting the procurement activities for these next stages. And for us, therefore, I would like to end with this document. We had in the November timeframe, end of November 2022, a ESA ministerial, and this ESA ministerial that proved and basically provided and gave us the go for the financing and the next step that this program can be realized. With that, if you go into the next slide, I would like to thank you for providing me the opportunity to outline what is the stages from the ESA perspective for the moonlight exploration. Thank you very much.
Thank you very much, Professor Werner. I think this session is run out of time. If you have question, I think our panelists here would happy to answer your question off the stage. And then, so I would like to end the session here. And thank you very much for your presentation and your information that give to us. Thank you.
Thank you very much, our panelists on the stage. Please give a round of applause once again, and thank you on this occasion. Okay, it's a very interesting of the information and the topic. Okay, and next we would like to invite everybody to the next session. The next session is everybody. We will go to the next sessions. Please invite to all panelists, including of the moderator. Please welcome to the first Dr. Ichii Mamoru is from Director General Radio Population Research Center Radio Research Institutes or NICT on stage. And then please welcome to Dr. Dr. Ichii Mamoru via online. And then please welcome Dr. Dinesh Mananta from the University of Tokyo on stage, please. And then may I announce to Professor Dr. Ponchai, Subnit School of Engineering, King Mongkut Institute of Technology, Lat Krabang. And then on this occasion, moderator is Dr. Sittiporn Chanunsin, Director of Space Technology Research Center of GISTA. Please welcome our panelists on stage and please start. Thank you so much.
Thank you very much for introduce and good morning, attendee, and welcome distinguished speaker for us today from on-site and online. Good morning, Ichii-san. Can you hear me? Oh, good. Thank you.
Yep.
So let's start from the slide, please.
Okay.
So today we have around 4 sections. The question is split in 4 sections.
So can I start?
No, not yet. Let me start from my slide first.
Okay. Yeah, sorry.
Just one moment, please. Yes. Okay, for the first question from here, we start from space weather impact, facility, and current research. So each speaker, we have time, each question around 5 minutes. Okay, please take care of this one. So just start from the Professor Dr. Ponchai first. Can you give me what space weather affects to our humankind activity and what your research area are working now?
Sure. Please go to the slides. Thank you. Okay, while we're waiting, I can give very short explanation. When we talk about space weather, we're talking about the path between the sun to Earth, which is quite a long distance. However, because of the sun size is over 10 times the size of the Earth, therefore, any events from the sun will affect Earth. There are different factors or different phenomena that will occur and then come to Earth. For example, if there are some solar flares that occurs or coronal mass ejection that occur on the sun, it will create solar wind. It will create there are some energetic particles and also some radiation, for example, X-ray radiation and UV. And the amount of time that it reaches Earth, for solar wind, it can be hours or days. But for some energetic particles, it can be like 1 hour, for example. And if you see from the screen, the Earth is very small, like a very small ping pong ball on the slide. Please click next. Therefore, the Earth will inevitably be affected, by these events. And if some potential impacts that are now understandable include the power grid lines. It will affect the aviation, satellite operation, and affect some different communication like HF, VHF, and UHF. And importantly, it will affect the accuracy of precise navigation and positioning. Next, please. This is an example of the effect of space weather on the recent SpaceX LEO satellites that was launched. Because they were parking at about 240, 130 kilometers from Earth. And at that time, there was a mild, meaning that not so severe space weather event. And they lost, I think, over 40 satellites, during this event in November 2022, for example. Next, please. In the equatorial region, in the low latitude region, there are also some disturbances, so-called equatorial plasma bubbles that occurs locally, but sometimes they are driven by the global events such as the magnetic storms and so on. And this disturbance, it will affect various applications as well, and they can be monitored using different instruments. For example, GNSS receiver, the VHF radar, or ionoson station, for example. Next, please. What are some of the effects? For example, will affect the spatial gradients due to the bubbles, will affect the operation and the integrity of the satellite navigation system, the aeronautical navigation system, such as GBus, for example. It will affect the performance of the PPP RTK performance, and also commonly known as the scintillation effects, that the satellite signals will have the fluctuation that may lose to the loss of logs of GNSS signals. Next, please. So you can see that it affects different types of technology that are involved. And what are we doing now in Thailand at King Mongkut Institute of Technology, Lat Krabang, with our partner university and institutes? We collect a lot of observation data and then create the portal called Thai GNSS and Space Weather Information Center that can give you the observation signal, observation data, and also some analyzed data products. And next, please. All the data will come to the server and then create data products. Next, please. This is another project that we work with Japanese agency, NICT. It is called Sea Lion Project. And basically in this project, it will monitor the ionospheric disturbance, also the plasma bubbles. And there are various instruments that are installed in this region, particularly in the ASEAN region. And we work together with 5 countries, and all the data also give a lot of understanding to this event as well. Next, please. This is an example at Chiang Mai. At the moment, we are at the location which is near this site called Mae Hia, and it has the ionoson station in collaboration with the Sea Lion project. It transmits radio signals to the sky 24 hours a day and gives the indication and how the plasma bubbles originate. Next, please. This is another station in Chumpon campus, which is in the south of Thailand. It's the VHF radar station. It's a very big station. It also sends the radar signals to the ionosphere all the way up to 700 kilometers from ground. Next, please. This is an example of data product. If you look on the right-hand side on the screen, it shows the occurrence of plasma bubbles or disturbance that occurs. So the red color will indicate this type of disturbance. And we would like to have the forecasting and warning capability. And how does it affect the technology? Next, please. This is an example of the data product that we produce. On the left-hand side, it shows the accuracy of the GPS signals in all over Thailand. In this case, it's the horizontal error, the maximum error, and 95% errors. And you can see that in one day, the errors are not the same at different locations in a geographic region. And on the right-hand side, we did some experiment on the RTK performance during the days with the plasma bubbles. And for this case, the baseline is 12 kilometers, which means that the reference station or the base station and the rover, they are over 10 kilometers apart. And we can see that there are some jump in errors for the horizontal errors and also the vertical errors as well. Next, please. And next, please. Yeah, sorry. Can you go back? Yeah, and so in this case, we cannot maintain the centimeter level accuracy. So during this disturbance, for the horizontal, the errors goes up to 3 times. And for the vertical, it goes up to almost 5 times of the 10 centimeters. Thank you.
Okay, thank you very much. And for the next question for the Dr. Ishi-san. Can you hear me? Can you still with us?
Yes.
Yes. So your question is, what is the goal and key milestone of space weather research and application in Japan?
Okay. Now I should answer this your question now or after my talk.
Yes, your question. You can share the slide if you want.
Okay.
Okay.
Yep. I want to share my screen. Okay, thank you for your introduction. So my name is Mamoru Ishii from National Institute of Information Communication Technology, Japan. So today, I'd like to update of Japanese activities for international operational space weather services. So today, I want to introduce 4 topics. Development of space environment sensors on next generation meteorology satellite Himawari. And the second one is the improvement of Gaia model for real-time data assimilation. And the third one is publishment of a national document for advancement of space weather forecast. And the last one is the international collaboration in space weather research and operation, Coimbra declarations. There are radiation hazard in near Earth space. Space radiation, which comes from outside the Earth, includes high-energy particles originating from galaxy and from explosive solar activities, such as solar flares and coronal mass ejections, and high-energy particles trapped in the geomagnetic field. Space radiation cannot reach on ground thanks to strong Earth's geomagnetic field and dense atmosphere. However, for astronauts and aircrew, radiation exposure can be a health hazard, and also for unmanned spacecraft flying around the Earth, space radiation can cause damage and spacecraft failure. So we established the project named CHARMS. CHARMS mission aims to simultaneous observation of space radiation and spacecraft charging at GEO. We have started a conceptual design of sensors since 2020. The Ministry of Internal Affairs and Communications and the Japan Meteorological Agency decided to support CHARMS engineering model sensor development in late 2021, and designing and manufacturing of engineering model have started. Development of flight model will start from 2024, and CHARMS on Himawari follow-on will launch in 2028. Next is the improvement of Gaia model for real-time data assimilation. Gaia is a project which combines atmospheric and ionospheric models for simulating global atmosphere-ionosphere. So real-time data assimilation system used Gaia enables us to nowcast and forecast of ionospheric condition, which is one of the final goals of space weather services. As input data, sun and solar wind, magnetosphere and ionosphere, and meteorology observation data will be used in real time. Next one is a consideration of improvement of space weather alert. The importance of space weather forecasting for stable operational of social infrastructure is increasing, as Professor Ponchai already mentioned. And outside of Japan, such as in the United States, there is a growing movement to prepare for social risks of space weather, such as evaluation of social impacts and announcement of national strategies. In Japan, as one of the science-based activities named P-STEP, the scale of space weather phenomena and their social impact on Japan were examined and summarized. On the basis of this work, the Ministry of Internal Affairs and Communication established a committee for the advancement of space weather forecast in January 2022 and published a report in June last year. In the report, we prepare the new scale of space weather. The purpose of space weather forecasting is to reduce the risks posed to social infrastructure by understanding and predicting hazard. Same as the analogy between magnitude and seismic intensity in earthquake, forecasts and alerts should focus not only on the scale of the physical phenomena of space weather, but also on the risk to social infrastructures. For this reason, new criteria of forecasts and alerts that take into account the social impact of space weather phenomena were considered. This is the last topic. I'd like to introduce another topics as international activities. So UN COPIO's Science and Technology Subcommittee to issue recommendations on space weather services in February last year. In this recommendation, three bodies of space weather community, COSPA, ICES, WMO is required to lead space weather related activities and has begun to consider. So September 2022, two representatives from each institution participated in this study at the University of Coimbra, Portugal. As a deputy director of ICES, I also attended these meetings. And we prepare a draft of Coimbra Declaration there. And now it's currently being discussed by various organizations. In this document, confirmation of the direction of the three institutions and agree on a framework, consider MOU, and pilot project, regular meeting, ground table, and so on. So as you know, there are a lot of international organizations related to the space weather. And the issue is, how do we make a solution to have the most effective way for all players? So each international organization has original object and goal, which should be respected. And some of the action plans can be collaborated among international organizations, avoiding duplicate works. And as a logistic matter, meeting period can be coordinated among international organizations. So now we start to discuss the actual action for cooperation and coordination among international organizations. Coordinate international organizations action plan and roadmap and plan joint project among these entities and arrange ground conferences. Okay, I'd like to answer the Sitipon Sensei's questions. What is the goal and key milestone of space weather research and application in Japan? This is my personal view, but I think one of the final goal is to provide nowcast and forecast of global atmospheric conditions, for example, density and electric field. Because there are a lot of users which related to the atmospheric conditions. So these information enable us to know the impact on radio communication, satellite positioning, and electric power grid, which are cause of the huge economic impacts. So thank you for listening.
Thank you very much for your question, your answers. So next, this from the Dr. Dennis, we have the why the cooperation is one of the key gain new knowledge, and anything else need to achieve the cooperation.
Yeah, thank you for the question. Okay, so our part is basically on capacity development as we belong to the academia and the research. So how to increase or develop the capacity in the field of space weather using GNSS. So this is very important. We already heard the two talks, how important is space weather for radio communication or other types of applications. And when I look at the presentations and this in the research field in the space weather, we see lots of the forecasting or the current computation of the TEC and some other space weather related things. But how to compute and how we can do and how to promote the know-how to do this type of data analysis is a key thing. And in order to do that, we need a GNSS receiver. And the receivers that are available for such data analysis are quite expensive. I think we need to pay at least $20,000, including the antenna and all. Sometimes the price goes even $30,000 or more. And that is not feasible in many countries in Africa, Asia, and also in some other countries in the South America. And that what we heard in the ICZ meetings when they did, because they were doing lots of training in Africa or other countries for more than 10, 15 years. But the capacity development is still very difficult. So we thought that maybe one of the bottlenecks is the receiver. And then since we are already working with the low cost receiver system for high accuracy, like this type of very small receiver nowadays available, the modules are available, but we need to integrate the system. And this can provide centimeter level with the RTK and using Madoka PPP, 10 or 20 centimeter accuracy. Then we thought maybe why not to use this type of very small and low cost systems to explore whether we can also do for space weather data analysis. And this is where it triggered us to explore. Let's explore whether this type of hardware can be used or not. At the moment, it seems that we can use, but we are exploring at the moment. And then we are trying to develop some sort of system integration by using the low-cost system. And here I put a slide here, how to make a low-cost system. So we are trying different options. And we have formed a working group in ICG, working group C in the capacity development. And there are a few members from different countries. And maybe some of you interested, please join our working group in the ICG. And we'll explore together what type of hardwares can be used. And other thing is that we need a tool, the software tool. So can you go to another slide? Yeah. And also we are exploring what type of tools are available, software available. And we would like to have an open source software, not just a binary. It's like a black box for us, and we can't implement for our low cost system. So at the moment, we are exploring what type of software is available, whether they are available at the source level, open source or not, and if available, for what purpose, whether we can compute only TEC, ROTI, those parameters, or whether we can also compute S4 index. So our target is a TEC and S4. These are two our targets. But as per our analysis so far, we believe that we can use the low-cost receiver systems, at least for TEC and ROTI. But for S4, some modules are there within the 1,000 euro. So I think that's possible. And we already contacted the manufacturer whether they can provide a special firmware to output the IQ power data so that we can also use for S4 index. So if it's possible, then I think we can deploy such type of system in large number, and that will be very good for training and capacity development and education. And this is what we need in the universities and training center, research centers. So we can have at least 10, 20, 30 even, and deploy in different places and use for training. And this is what we target. And the next slide, also exploring whether we can use the smartphone chipsets itself. And last year, we had the presentation from Google, and Google, already made the APIs open for logging the raw data. And now we also contacted them and wanted to know, we want to do the space weather related data computation. Is it possible? And they provided some samples and some ways to analyze the data. So we are still exploring how to do this. But anyway, it's like the box is open. So we need to find out what are inside the box and how to use those items to meet our requirements. So this is what we are doing. So our target is to make low cost device systems and to promote this technology, capacity development, and explore the available software, including the smartphone devices and so on. Thank you.
Thank you very much. It's quite interesting to do the low cost GNSS receivers. So for the next question is for Professor Ponchai, is about based on the ICAO, what is the space weather impact in Thailand?
Okay. Slide, please. Okay. So from what I heard is that ICAO is also very active and also serious in the role of the space weather events on aviation. Next, please. And over the past decade, ICAO has drafted various documents and also had international meetings with various international organizations on this issue. And in order to prepare the aviation for space weather impact, so they look at this type of relationship between the impact on Earth and also the frequency of the events, the probability of how often it occurs. So if you look on the slide, the bottom part, there's this red area. So these are the very strong type of the space events. For example, back in 1859, the event was so-called Carrington event. And they said that it happens every 100 to 500 years. And at that time, on Earth, it was still the telegraph, era. So it's not like today. But the situation at that time, mostly from visual and also the effects on telegraph system was so severe that even the aurora that normally occur in the northern hemisphere, a very high altitude latitude, people could see in Florida or in the Caribbean, which was very unusual. But the probability of happening this type of event is low. However, it's still possible. The yellow part explain about they call severe to extreme events. An example of this event is the Halloween event in 2003 and also Quebec event in 1989. And at that time, there was also very strong solar flares and solar storms that affected the power grid failure. And for example, in 1989, half of the country, the power station malfunctioned. And then, of course, there are some, for the green area, there are some more milder space weather events that occurs. It is more often, but it's not so noticeable. But it may affect the capability and the performance of various systems. Next, please. So for the impact of space weather on aviation, they look at different types of systems that can be affected. For example, in communication, it can affect the loss of HF and VHF signals. It can lead to the loss of GPS at above 82 degree north latitude, which is the vulnerable area. You can call it the polar areas, that are more affected. And normally this type of GPS effects will cause the diversion of flights to a more southern latitudes. And anyway, and for navigation, it can lead to erroneous positioning. Some avionic or equipment can be affected. Some sort of failure due to single event upsets, for example. And also importantly, as Dr. Ishii-san mentioned earlier, the radiation is also one of the consideration in aviation, that during the extreme space weather events, it can enhance the exposure of radiation to flight crews and passengers. Next, please. And that's why ICAO itself recently came out on the manual on space weather information in support of the air navigation. And an important part of this, the ICAO activities are twofold. One is to assign the space weather data center. I think it's called warning center of sort, like the regional warning center. And at the end, as of I think November 2020, 3 operational centers were established in the world. Mostly come from different continents, but there's some combination of sort. And the other aspect from ICAO activity is on the advisory. As you know that nowadays for aviation, the advisories are often announced by the airlines or the radio operators for the aviation, particularly about the situation in the airport, about the climate, about the storms. But for the space weather advisory message, this is related to the three areas that we looked at earlier. One is on the communication, another is on GNSS operation, and the last one is on radiation levels. And that's why it means that not only for scientists that need to understand this type of advisories, the airline operation and also the pilots, they need to understand this advisory as well. Next, please. And lastly, this is related to one area, which is called ground-based augmentation system. As mentioned by Professor Rizas yesterday, that the important part of GNSS, the evolution now is on the augmentation system, and aviation also is an area that relies a lot on augmentation information. Why? Because the aircraft needs to identify the position, normally using GNSS technology. However, due to various erroneous noises, disturbance, and so on, the GPS satellite will go through the ionosphere and troposphere, which create some sort of fluctuation and disturbance. So that's why in GBUS technology, for example, it is used for approach and landing. In order to improve this accuracy and integrity, in the standard, the reference stations have to be installed and then send the correction information. However, in order to implement such a system, some countries implemented such a system without a thorough study on the effects of this ionospheric disturbance. And oftentimes they are unoperational at nighttime because of these disturbances. So it is important that recently in Thailand, for example, we had a 2-year project to implement the GBUS technology and study, I think together with JICA as well, and with the Thai aviation agencies. And one of the part of the work is to study on the effects of space weather on the accuracy of the GBUS system and whether it's above the limit or not. Next, please. I think this is the last slide. This is an example from the result that shows the difference of delays between two locations, or we can call it spatial gradients. So during the events with bubbles, with the disturbance, the difference in delays or spatial gradients show large values. In this region, it's still not so as dangerous as in some other region. In some other region, like in Brazil, for example, these jumps in these gradients, it is beyond the scope or the allowable values in the ICAO standard. So that has to be taken into consideration during operational phase. Thank you.
Interesting. Thank you very much for the answer. So for next, we have in part of the cooperations. And so the question is here for Dr. Dennis. Okay, but based on your experience, what are the key to convince or support policy maker in the space weather impact?
Okay, so as I explained before that as academia or research, so we and also the importance of the space weather, we need to have a capacity development. And again, that same problem exists. So how to make the cost of the system very, very low. And this is one part we need to think. So in this related to your question, so I have 3 points. So how to make the cost low, I mean, low cost system. So we need to talk with the receiver vendors or manufacturers to make it available at a lower cost by providing some specific features, or already some makers, they already provide some features, but probably the users don't know as well. And the space weather, the research is basically done by people in the physics and scientific community, whereas the signal processing is done in the GNSS side. So I also see a gap between the two communities, the scientific community and the GNSS, the signal processing, the GNSS, the core GNSS team here. So probably we also need to teach the scientific community that these type of receivers today are available and it can be possible to meet your requirements. So this is one thing we need to tell them. So we need a collaboration on that between the two. And somebody has to coordinate, maybe the policymakers, and they should be involved as bridging the gap between the two communities. That's one thing. And then the system that we develop should be very easy to use and very easy to deploy, because most of these systems are installed in different locations. Sometimes those areas are very difficult to access. And some areas, they don't have even the electricity or other communication links. And we are exploring some of these areas as well, how to deploy the receiver in those areas, in such remote areas where we would like to keep the device. So the thing is that how to make the system very simple, automatically working. So anybody without the knowledge of GNSS can deploy the system, set up the system. So you just connect the cables, antennas, and put the power on, and it should work. So there's some sort of automation on the installation side, setup side, and the data logging as well, how to log the data automatically. And it should be done the predefined parameters, and the scientific community should tell us how this should be done, what type of data at what level should be observed, whether it's for real time or post-processing. And then the data analysis part is related with the software and the tools. We need to explore on that. Yes. I think, yes, that's all from my side at the moment.
Okay, thank you very much. For next question for Dr. Ichi-san. Can you give me some suggestion to advise you said about the International Space Environment Service, ISES, in your previous presentation? How maybe some guys in here or some country want to join? Thank you.
Okay. Yeah, thank you, Stephen Sensei. So I want to answer like that. So as ISIS, actually, ISIS has quite a strict policy for joining as a regional warning center. And the candidates shall have at first endorsement by the government. The second one is the evidence for space weather services to the domestic users. The third one is sharing and exchanging space weather data with other regional warning centers in freely and timely. So I strongly suggest you that Thailand country should start the services, domestic services for providing space weather information for your domestic users. That's the first step. I think you already have an endorsement by a government. And the third one is it also needs to time and some budget to establish useful data archive and data sharing system in real time. Anyway, I'm very happy to contribute to improve your system, including joining ISIS. Thank you.
Thank you very much for your suggestion. They appreciate your answer to advice. And come back to slide, please. So have a little bit to present about the corporations. Recently from Thailand, from GISTA and SC2, we have the MOU together. And we have the opportunity from NSC to let us to visit in NICT to do the research and the training for space weather forecaster. So it's happened in the end of last year, around November to December. Yeah, this is the team from Thailand to join in ICT. The next slide, please. And also Thailand have represented by JISDA. We have chance to visit in ICT on October by our executive director to meet the president from the NICT here. In this, I would like to thank you very much for NICT to the very good support us in many ways. We for do the research and do the space weather forecast service in Thailand. Next slide, please. For the last topic today is a support, maybe support from the government or the policy maker or researcher or between international support. Let's start from Dr. Ponchai. Yes. What you expect or support from Thailand, the government unit for space weather research or maybe share international, including the facility, capability or technology, including the budgets.
Wow, I mean, research costs money, right?
Yes.
I think for the governmental support at the national level, in Thailand, we have the National Space Committee. I think as JISDA, I understand that JISDA is the secretary to this space committee. I think JISDA should help push for the agenda on space weather awareness and also the space weather event readiness plan. We need to have some white paper in order to understand the scope of the severities, and we have some contingency plan, you know, to cope with some severe events, even though they rarely occur. So that's the first thing. And yeah, I would like to congratulate JISDA on going to establish the Space Weather Forecasting Center in Thailand as well. In terms of facilities, as you know that for the observation of space weather, it requires various type of instruments and coordination and data. It also costs a lot of money, right, for maintenance and so on. I understand that JISDA recently also installed magnetometer as well, right? So I mean, we would like to have the continuous support from government or from JISDA on this type of facility maintenance and also upgrade. So that's important. And importantly, another aspect that we haven't talked much about during this conference. In Thailand, we studied the GNSS infrastructure, and I believe there are over 200 stations all over the country. For scientific study, we need a lot of data, you know, going through various decades. And the data backup policy and storage is actually paramount to the success of science. Therefore, I encourage that JISDA, which is also, I think, one of the backup entity, right, for the GNSS infrastructure in Thailand. We need to collect and store this data and probably implement this open data or open science policy as well. For space science, because a lot of events occur according to the solar cycles, which last from 10 to 11 years, meaning that each cycle lasts that long. That's why we need a lot of data going back many decades. So we hope that with a lot of GNSS data that are produced every second as of now, all these data are stored appropriately for this purpose. Thank you.
Thank you for the answer. Let me a little bit give more information. So right now, at JISDA, we working on to do the National Space Data Center. It's one of the data is in the GNSS as well here. And it's good news. We have tried to gather all data we have in free anything, and it's free. You can come here to download them for support the researcher and the scientists. For the next question for Ichi-san, what do you expect all the corporate Thai research or scientists or the government unit or support from Thailand or other nations?
Okay, thank you. So the third question, I want to answer this. Now, as I mentioned in my presentation, there are various number of international organizations related to space weather. But the Asian role is very important in the field of space weather operational services. But in the present status, the number of players from Asia, especially from Asia, are too few. So I eagerly ask you to join us in international organizations and discuss the international corporations together. Yeah, that's my answer. Thank you very much.
Okay, maybe the last question for the Dr. Denish. Maybe the same question, how you support all the cooperation. I think you have some answer for the previous question. Maybe you have something more to additional answer.
Okay, just a very few lines. So our request or the cooperation from Thailand is that please help us to do our evaluation or the exploring the low-cost systems and exploring the software and that's data analysis part and also the data logging part because you already have so many stations in Thailand. And if possible, we want to co-locate our low-cost system using the same antenna and log the data with the receiver that is being used for space weather. And we'll put side by side our low-cost system and log the data and compare the results, how good or how bad. So if we get a reasonably good data using the systems that our prototype systems that we have. So if the results are acceptable, maybe we can then say, okay, even this type of system is at least good for capacity development, training, education, and all, and some pilot projects around the world, and can be accelerated maybe by deploying large number of units. And that this is very important because the space weather is not only local or regional, it's a global issue as aviation. So aircrafts are flying and they want to avoid the high scintillation area or the ionospheric affected area. So it's flying a long distance. So how to do that type of route planning is very important. So it should be a global problem address. Thank you.
Okay, thank you very much. I have a little bit to forget to present. So right now, here a little bit, maybe 30 seconds. Right now, national roadmap, like Professor Ponchai said, is the Earth Space System for Frontier Research. Next slide, please. So here is define the milestone. One of them we focus on the space weather research on the space safety and security on the red box. Next slide, please. Next slide, please. Yeah, this is a national roadmap. So right now is the agency, the funding the agency just accept this one. So maybe in near future we have the correct milestone for the Thailand to do in space weather research. And next slide, please. And the last one is National Space Master Plan just already accessed from the cabinet. We also have include the facility budget. Next slide, please. And research area in the space weather in the green box here. We have strategy in here, including in space weather research in Thailand. So that's I would like to present what Thailand we have also this one to support to do space weather research, and also we have other area as well. Okay, thank you very much for today, and thank you for distinguished delegate from the on-site and online. Thank you very much, Ichi-san, Professor Ponchai, and Dr. Dennis. Thank you very much. Thank you.